Hi everyone, this is Dr. Nitin Kumar Saxena presenting the second lecture on the topic of Kirchhoff's law. In previous lecture, we have discussed the various fundamental terms which are used in network studies. And now the question comes that when we are going to solve any network, an electric circuit, then we require some law, and this law is given by the scientist Kirchhoff, the basic law which is given by the Kirchhoff, and hence these laws are called Kirchhoff's current law, in short KCL, Kirchhoff's voltage law, in short KVL. These laws are applicable for all the circuit elements. It may be resistance, it may be inductance, it may be capacitance. But for making our life simple, the calculation simple, we will start with resistance only. With DC circuit, that source, as we have studied in last lecture, that sources may be two types, voltage source and current source. But these sources may be AC type or DC type. But in starting we will go for DC type, and hence we will study the DC circuit, sources having DC source, circuits having DC source with resistance only. So with this, let us start by recapping the two important things: the difference between the loop and mesh, and the difference between the node and junction. Then we will give you the definition of KBL and KCL. So in a very fast way, let us a simple circuit. Let us a simple circuit. Here is this one. The circuit has V1 voltage source, V2 voltage source, R1, R2 and R3. So this is a basic circuit having two voltage sources and three circuit resistances in this circuit. So the total components in this circuit is 5, out of which 2 are the sources, voltage sources, and 3 are the resistance as a circuit element. So now let us see the point A, B, C, D, E, F. So if I take a closed path A, B, C, D, E, F, A, the first big one, A, B, C, D, E, F, A. In the second, A, B, E, F, A. This A, B, E, F, A. Similarly, we see the 2 points. Suppose point A and suppose point B. So I just want to check that loop and mesh, here node and junction. So according to the definitions which we have studied in my previous lecture, the loop may be both closed path are the loop. So both closed path are the loop. But the big one cannot be a mesh, because when we take this closed path, then inside this closed path we have two closed paths. So it cannot be a mesh. So it is not a mesh. But here when we are talking about this is a mesh. So this is a mesh, right? In a similar way, we see the point A and point B. So point A has no diversion. Whatever the current flowing from one side will go in second side. So there is no diversion, and this node may not be a junction. but B has a divergence, so B may be a junction. While we talk about the nodes, though, both are the nodes. So this is the recap for the definitions of mesh, loop, node and junction. After that, let us start with the definition of KCL and KVL. So let us start with the definition of Kirchhoff's current law, which is in short is given by KCL. You see here, mathematically, the sum of I is 0. What does it mean? It means, let us see the simple thing over there. Let us see the simple thing over there, that if we are talking about a junction B, then what will happen at junction B? At junction B, we have at B we have three branches are connected. 1, 2, 3. So if three branches are connected, so there would be how many currents? Say 1, 2 and 3. Three branches, so three currents are going from one side to another side. I am not talking about the direction now. That we will discuss later. So you see the current in all the three branches are I1, I2 and I3. If I sum all the currents at point B, it should be 0. And this sum is denoted by this symbol, and when we are adding these three, then sum should be 0. In short, we can say that according to Kirchhoff's current law, the sum of all the currents at the junction should always be 0. Keep in mind, the sum is an algebraic sum. So we can define our definition and we can say the algebraic sum of the current at any junction is always 0 according to the Kirchhoff's current law. If suppose, for example, I am saying this is in plus, this is in minus, this is in plus. So the algebraic sum means we will consider the sign of I1, I2 and I3. This is called algebraic sum. The detail we will see when we are going for the method how to solve the problems using KVL and KCL. Up to this point, we are only understand that algebraic sum means that whatever the current we have, we will include their polarity either plus or minus also, and the sum of all the currents should always be 0. Right? Now, after this Kirchhoff's current law, let us see what is the Kirchhoff's voltage law, KVL. Again, you see summation of B is 0. So summation of B 0 means that for any closed path, when we move for any closed path, then the voltage across each component we will consider, and the sum for them should always be 0. And here again, the sum should be an algebraic sum. Let us see again through this example. Suppose I am talking about a closed path, and you see here we are talking about the closed path, and closed path means we can take loop and we can take mesh. So KVL is applicable for both loop as well as mesh. So if we are talking about the closed path, big one, A, B, C, D, E, F and A. So this means we are moving from A and reaching again to A. We cannot leave up to F. If we are leaving at F, so we are not closing the path. So the process is, for your Convention, for your better understanding, you always start from the point and move and finally reach to the starting point. Then you can say that your loop is a closed path or mesh is a closed path. Is it okay? So when we are talking about this closed path loop, the components are B1. Sorry, we are starting from this point. So components are R1, R2, B2 and finally B1. So the components are R1, R2, B2 and B1. Right? So we have in this closed path, we have four components R1, R2, B1, B2. For these four components, let us say the voltages are V1, V2, V3 and V4. So the voltage across each component is B1, B2, B3, B4. So what does your KVL say? Your KVL say that sum should be 0. So sum should be 0 means V1, V2, V3, V4 we will add algebraically. Algebraically means whether the polarity of the voltage you have to take either positive or negative. For example, I am supposing this is positive, this is positive, this is negative, this is again positive. So algebra, now do the algebraic sum and it should be 0. So in any closed path, the algebraic sum of all the voltages must be 0. This is called KVL. I'm again telling you that which one will be positive, which one will be negative in this case or in this case, that we will see later when we will try to solve numericals or at the time when I will tell you the methodology used to solve the problems using KVL and KCL. So starting uh, this can be done with an example. So let us start with one circuit, the same circuit we are going to solve. And for the same circuit, what would be the steps that we will keep in mind for applying any KVL, that we will see step by step. So the first point is that when you are going to apply KVL, Kirchhoff's voltage law, in any circuit, then what you will do, first of all, you will choose any one voltage source of your choice. Suppose here in this circuit I am saying there are two, maybe more than two voltage source. So if there are two voltage source, choose any one voltage source of your choice. Suppose I am choosing the voltage source 1. Okay. So from case 1, choose the voltage source and here I am choosing the voltage source 1. So first point is choose any voltage source. Right? After this, now you start to note or to give the flow of the current in the circuit. Here I am starting like this. Suppose the current is going like this. From here I am saying the current I is going. The same current will come here, I. The same current when will come at this point, it will divert, and I am saying that suppose I1 is going here, so naturally I minus I1 will go there because the total current is I1 is going here, then I minus I1 will go here. You may ask a question that why I am taking this current is going here. Current can also go like this. I am taking the current is going downside. And the question may come in your mind that this current may also go up. But since I am only assuming, so this is my assumption that current is going downward. If the answer is opposite to my assumption, obviously the answer will be in negative. But as far as my assumption is concerned, so I am free to choose anything which I want. And what I want in this case, I want that yes, current I is coming here. So some part is going there and rest part is going there. So if I current is coming here, I1 is going down and rest I minus I1 is coming to this side. Is it fine? Then the same current I minus I1 will come here, will go like this, will go like this. Here it will be I minus I1 and here will be I1. So the total current when you will see here again will be I and finally there will be I. Okay. The second point is start flow of current in complete circuit. In complete circuit. The important thing is that if your this second point is correct, you are flowing the current correctly in the whole circuit, it can be checked that if the current I is you are assuming going from this voltage source, then the same current I must come at this voltage source. You getting that? What I am assuming? I am assuming that from the voltage source V1, the current I was going out. What current this voltage source was giving? I. So when you will complete the assumption, the flow of the current in the whole circuit, finally the same current should come at this voltage source. If it is so, then your second point is correct. Otherwise, you have to check it whether you have make a mistake to distribute the current in the whole circuit. Since we are okay here because our current I is going out from this positive terminal and same current is coming at negative terminal, so we will say we are correct for the second point and now we can move towards third point. So what is the third point? Third point is that now show the polarity of each component in the circuit. You see in the circuit we have two components. One is element, resistance element, and second is source, voltage source. So for each and every component which is existing in the circuit, you have to go and you have to make the polarity. How can you do this? For doing this, you have to keep in your mind that show the polarity of each component. Current then pot flows higher potential to lower potential always across circuit element. So this is the important point. When we are going to make the polarity on the circuit components, then what you will keep in your mind, that current always flows from higher potential to lower potential in any circuit element. So if you see this, how can you make the polarity now by using this convention? You see, for R1, for R1, the current is flowing in this direction from A to B. So it means since the current is flowing from A to B, this point is at higher terminal compared to this. So what we will say, this is a positive then if this is a positive, then it would be negative. Again I am saying this is totally depend on my assumption. This is positive and negative according to my assumption. As my assumption is opposite, then when I'll find the answer, it will give negative value. But I'll go according to my convention. And my convention is that since the current is flowing from A to B, so obviously A side of this resistance will be plus and B side of this resistance will be negative. Again, same concept here. If you see that current in resistance R3 is coming downward, so naturally this will be positive, this will be negative. And here the current is I minus I1 is going from B to C, so this is positive and this is negative. So in this way we can note down the polarities at each resistance which is connected in the circuit. And after this you see that we have two voltage source. So naturally the voltage source polarity is given here. This is positive, this is negative, and this is negative, this is positive. If you want, then you can write again. Otherwise, no need to write again. Right? So this third point is okay. Third point is over. What is the third point? Show the polarity of each component. After this, the fourth point is now for choose closed path and write KPL. Apply KPL. Choose closed path and apply KPL. So now you see that choose any closed path. So I am choosing one by one. So first I am choosing the small, the A, B, C, A, B, E, F, A. So A, B, E, F, A. So in this A, B, E, F, A, you see we have one resistance R1, we have resistance R3 and voltage source B1. So what is the voltage across R1? And the voltage is IR. So the current in this R1 is I. The value of the resistance is R1. So the voltage across this resistance can be given by IR1, right? Similarly, the voltage across this resistance R3 is I, current is what? I1. So the I1 into R3. And here, what is the voltage? Obviously, the value of the given of the voltage source V1. So the value of voltage is IR1, IR1R3 and V1. And now when we will put in the equation, so we have to keep in mind that we will also write algebraic sum. So algebraic sum, obviously, if you move from plus to minus, you will take. This is again your assumption. If you are taking plus to minus plus, then always take plus to minus plus. Otherwise, opposite you can take. So what I am saying, if I will move from positive to negative, then I will take positive. If I will move from negative to positive, I will take negative. So let's see here. My loop is A, B, E, F, A. So how I am moving? I am moving from A, B, E, F, A. So when I am going from A to B, the voltages I are 1 and I am going from positive to negative. So I will take this as a plus. Is it okay? Again, now I am at B. So go from B to E. When you are going from B to E, what is the value of voltage? I1 R3. The value of voltage is I1 R3. But since I am moving from again plus to minus, so what I will take? Plus. Now again you go like this. There is no soul component, so leave it. Come from F to A. When you are going from F to A, the voltage value is B1. But we are moving from minus to plus, so what I will take? Minus. So all the things are clear and all the things are covered. So finally the sum should be 0. Is it fine? So this equation is written for this closed path. This equation is a KBL according to KBL, Kirchhoff's voltage law. Let us again repeat it with another closed path. The another closed path is suppose I am taking again, but for understanding I am taking the opposite direction. So opposite direction means here we move in clockwise direction and now I will move anti-clockwise direction to understand the concept. Okay, so if and both are possible, I can go by clockwise also, I can go by anti-clockwise also. So for giving you the better knowledge, better understanding, I am again taking the anti-clockwise side. So when I go anti-clockwise side, so suppose B, E, D, C and B. So for this B, E, D, C, B, let's see here. I'll move from B, we'll go till E, then D, then C and again at B. So when I move like this, so what do you see? In starting, we have R3, the value of voltage is I1 R3, then V2, and here the voltage is, the resistance is R2, current is I minus I1, so voltage is I minus I1 times R2, right? So let us start to write the equation. So from B to E, the voltage is I1 R3. Now you see, I am moving like this, so I am moving from positive to negative. So what would be its value? Positive. Now E to D, nothing. D to C, voltage source. So voltage source value is a voltage source value. And what is the voltage source value? V2. And we are moving from positive to negative, so this is V2. At point C to B, the value of voltage sources, voltage is I minus I1 into R2. And since we are moving from minus to plus, it would be minus. And all the terms are taken. So finally, the sum, algebraic sum, should be 0. Is it fine? Again, for more understanding, what I am doing, now I am taking the same loop, but since this time I took anti-clockwise, now I will take clockwise and see what will be the difference. So if I take again, so for taking this, let us see what will happen. See, so now I am taking the same loop, but in this case I took anti-clockwise. Now I'm going to take clockwise. So when you take clockwise, then what you will write? B, C, D, E, B. Right? B, C, D, E, B. So when you move like this, so I'll do now somewhat fast. So from B to C, the value will be plus, because we are moving from plus to minus, I minus I1 into R2. Here, what is this? Voltage source. The value is minus V2 because we are moving from minus to positive. Here, we are moving from minus to positive. So, minus I1 R3, and this is equals to 0. If I multiply the whole equation with minus 1, what I will get? What I am doing? I am multiplying this with minus 1. So what you will get? Minus times I minus I1 R2 plus V2 plus I1 R3, and this is equals to 0. So you see, now you compare this equation with this equation, both are same. What does it mean? It simply means that the solution will remain same whether you move clockwise or whether you move anti-clockwise. The method of writing the expression will be different. The expressions will look different, but finally you will get the same result. Is it clear? Again, I'm writing the last KVL equation for the big loop. And for this big loop, I'm moving, suppose again I'm moving clockwise. So when I'm moving clockwise, so this A, B, C, D, E, D, E, F, A. Right? So for A, B, C, D, E, F, A. Right? So again, please try to write the KVL. Then what will be the KVL? Start from A, move like this and go up to A. So from A, when you start, what is the value? IR1 with plus sign, because this is going from positive to negative. Between B and C, we have R2. The current is I minus I1. So I minus I1 R2. Again, we are moving positive to negative, so positive. Therefore, after getting all the equations, now we can solve these equations to find the value of different variables like I1, I2, I3, or whatever the value. Suppose in this case we have the values I1, and we can solve these equations. By solving these equations, we can find their values. Once we got the values, then we can get the value of the current through any resistance, and similarly the voltage across any resistance. For example, if we see the resistance R1, then the current going in resistance R1 is I. So the current through the resistance R1 is I, and the voltage across R1 is I into R1. So for each element we can find the value of voltage as well as current. So for this lecture I'm finishing, and I hope you have understood the how we can apply the KBL and KCL for different circuits. In next lecture we will try to solve one or two problems using KBL and KCL. Thank you very much.